So section 5.7 is on the topic of finding what are called roots or zeros, and that basically means finding the solutions of a polynomial. So a couple of things we want to accomplish. First of all, just define that term zero, root, or solution. That shows up a lot when you're solving polynomial equations. Second question, how do you find zeros? And that will be using techniques that we've kind of talked about already, things like factoring and other things early on in the chapter. Third thing is, what is Descartes' rule of signs, meaning positive and negative signs? How does that apply to polynomials? How does that help us solve them? And then finally, if somebody gave you the solutions, if you're working backwards, if they gave you the solutions to an equation, how would you go backwards to figure out what polynomial that you started with? Alright, so here are just some terms that all kind of mean the same thing. If somebody says, for example, let's suppose you have, we'll do a real simple one. Suppose you have this quadratic equation right here. We'll make that 8x plus 12 equals 0. If you were to factor this, you would get x plus 6 times x plus 2. And there's a couple things that mean the same thing, basically. X equals negative 6 and x equals negative 2. Those are both called zeros or solutions or roots, because if you plug in negative 2 here for x, or if you plug in negative 6 here for x, in both cases you would get 0. So the word zero for the root or solution basically means the same thing. If you were to graph this as a parabola, you would have x-intercepts at negative 6, because that's what that means, that there would be an x-intercept. Negative 2 would be another x-intercept, and you'd have parabola looking roughly like that. And what it also means, if this number c, like in our example, if negative 6 is a root, and that means x minus that number, x minus negative 6 or x plus 6, that is a factor of the original polynomial. So if negative 6 is a root, x minus negative 6 or x plus 6 is a factor. Same thing here, if x equals negative 2 is a root, then x plus 2 would be a factor. Those all are just equivalent terms for the same thing. Alright, then we have something that it sounds fairly important. It's called the fundamental theorem of algebra. It basically says every single polynomial has at least one solution in the set of complex numbers. Complex numbers meaning either real numbers or imaginary. And later on we'll go on to say that every polynomial with any degree, its highest degree, will tell you how many zeros it has. So for example, if you had this polynomial right here, later on we'll learn that because the highest degree there is 5, that means that equation is going to have 5 solutions to it. Some of them might be real numbers, some might be imaginary, but it will have 5 solutions. Alright, so let's prove that, or not really prove it, let's verify it with several examples. So this is we have x being raised to the second power. So according to what we just said, there should be 2 solutions, so we'll be able to factor this. And we want numbers that multiply to 9 and add to 6. And that would be 3 times 3 is 9, 3 plus 3 is 6. And so in this case we're going to have the root negative 3, and we'll also have negative 3 here. So really it looks like there's one solution, but we'd actually say there's one double root, because negative 3 is counted twice. So it does satisfy what we said about x to the second power having 2 roots, one double root, and obviously both of those are real numbers. So if you graphed it, it would look like this. You have this right here, it only crosses once, but it's being counted twice, because in theory, you could write this whole equation right here as x plus 3 to the second power. So negative 3 is being counted twice. Okay, this one right here should have, according to what we said, it should have 3 roots, because x is being raised to the third power. So if we look at this, there's only 2 terms, but they do have a common factor. They both have an x in common, so we could pull out an x, meaning divide by an x. X cubed divided by x is this. 25x divided by x is this. And then we can solve each of these. So this one, the only way to make that 0 is if x equals 0. There's one solution. This one right here, if we set this equal to 0 and solve it, we would subtract 25 from both sides. We would get x squared equals negative 25, and then to solve we would square root both sides. In front of a square root always goes plus or minus, because there's 2 things you could square to get any number. One is the positive version of the number, one is the negative. So in this case we have x equals, well, the square root of 25 is 5. The square root of negative 25 would be 5 times the imaginary number 5i. And you could have plus that or minus that. And the faster way to write it is just plus or minus 5i. So let's notice we have three solutions. X equals 0 is 1. X equals positive 5i. X equals negative 5i. Those are the second and the third, and that matches up with what we said. When we said x is being raised to the third power, it should have three solutions. Only one of them is real, though. The other two are imaginary. So in the graph, what that looks like is it only touches at that one real solution, and the imaginary solutions don't appear on the graph, but they are considered solutions. Alright, a couple more. So 1b is actually a difference of squares. And let's recall, what did we multiply to get x to the fourth? It had to have been x squared times x squared. It's called a difference of squares. Difference means minus. X to the fourth is a square. It's x squared times x squared. 16 is also a square. It's 4 times 4. And then how do we get the minus? Well, one of these has to be plus, one has to be minus. If we solve both of these for x, we'll set that equal to 0. And subtract 4, and then square root. And same thing right here, we would set this equal to 0. And solve that by adding 4, and then we square root. So this one is going to be positive or negative 2. This one, because it's a square root of negative 4, will be positive or negative 2i. So notice it's x to the fourth power is what we started with. We end up with 4 solutions. Positive and negative 2, positive and negative 2i. That's 4 solutions. Alright, we'll come back to C. Let's look at option D right here. And if you look at this, it looks like there's 4 terms, so we'd want to use what's called factor by grouping. And that means grouping things into groups of 2. So I'll split this down the middle. 3x cubed and x squared, it looks like they both have an x squared in common. So let's divide that out. And if we divide each of these terms by x squared, that first one is going to be 3x minus x squared divided by itself is 1. And now if this works out, we want to see if we can get the same thing appearing in this other parenthesis. So it looks like these both have a 3 in common. We can divide out by 3. 9x divided by 3 is 3x. 3 divided by 3 is 1. So it does turn out to get the same in both parentheses. That's a good sign. And now 3x minus 1, that's a common factor for both of these. So that means we can pull it out in front. And then the other parentheses will have x squared plus 3. And that's going to equal 0. So if we look at the beginning, x is being raised to the third power. It means we should have 3 solutions. And let's see if we can find those right now. So 3x minus 1 equals 0. That's going to be 1 solution. So if we add 1 to both sides, we get that. And we divide by 3. X equals 1/3. There's our first solution. That's a real solution. Let's see what happens here if we set this equal to 0 and subtract 3. Here we get x squared equals negative 3. We'll square root both, and we always put a plus or minus in front. So x is going to be plus or minus root 3. So because of this negative, we can write root 3 like this. We can write root 3 as root negative 3 as root 3 times root negative 1. And another name for root negative 1 is I. So that's what we could write, a plus or minus I root 3 that has 3 solutions. One is real, and those 2 imaginary solutions are obviously imaginary. And something that's interesting, what we'll talk about later, is imaginary solutions always come in pairs. So you always have either 2 imaginaries or 4 or 6. You always have an even number. They have to go together. Alright, this last one is probably the trickiest one. So at first it looks like it's going to be factored by grouping, and actually that is the way we need to solve it. But it's not obvious how to group. If you try to pull out a common factor from these two, you wouldn't get the same thing in parentheses as with the other two. So here's how you can do this. You can actually split this up. So we have x cubed, we have 4x squared. And then if I look at the 10, it would be nice if there was something that I could factor out of 10 and somehow break up that 7x. And ask myself, what is it that 10 has in common with something that's almost embedded in 7x? And the answer would be 5. If that were 5x instead of 7x, well, then I would be able to factor something. Okay, so let's break up minus 7x, let's break that up into minus 5x minus 2x, because that's what 7x equals, minus 5x minus 2x. Okay, it's not obvious how you would do this. You need to kind of have seen a couple of these problems to know about this technique. And now we can factor by grouping. Now if we look at this right here, this has a common factor of x. All 3 of those terms. If we pull out an x, divide each of these by x. X cubed divided by x is x squared. 4x squared divided by x is 4x. And then minus 5x divided by x is minus 5. And then we could even factor that further, because this is a trinomial right now. If we look at it, we want numbers that multiply to negative 5 and add to positive 4. And one of them has to be positive, one has to be negative. That's the only way you get a negative right here. Positive 5 and negative 1, that would work. So that is now completely factored. Okay, let's see if we can make that happen in the other one. So with these two right here, they both have a negative 2 in common. So if I divide negative 2x by negative 2, I get x. If I divide negative 10 by negative 2, I get 5. Let me just rewrite it right here. And now you may notice that we do have the same thing in both parentheses. They both have an x plus 5. So let's see if we can factor this further. So we will pull this out, because that is a common factor. And then how do you write what's left behind? Well, what's left behind, just use a different color so we can see a little bit better. We have this x times x minus 1, and then that minus 2 right there. So that's going to work like this. It's going to be x times x minus 1, and then we have the minus 2. So let's continue to simplify that. We still have x plus 5 right here. We multiply this out, x times that, and we distribute, it's going to be x squared minus x, and we still have that minus 2. Again, this is equal to 0. And now we should be able to factor this even further. We have x plus 5. Then this is going to be numbers that multiply to negative 2, add to negative 1. So 1 has to be positive, 1 has to be negative. And the only numbers that multiply to 2 are 2 times 1. The 2 has to be negative in order to make that FOIL correctly. So now we have three solutions. We have x equals negative 5, that makes this parenthesis 0. X equals negative 1 makes this parenthesis 0. X equals positive 2 makes that parenthesis 0. So we have 3 zeros, and let's go back and check it. We started out as x to the third power. So we should have had 3 zeros, and we did. And they're all real numbers. Okay, this is kind of something we already mentioned. Basically, it's the fundamental theorem of algebra, just a little extra part of it. It basically says anything, a polynomial that has degree n, meaning the highest exponent, has exactly n roots. So something to the third power has 3 zeros, or 3 solutions. Something to the fourth power has 4. Something to the fifth has 5. If it were this equation, x to the 100th, that would have 100 solutions, or 100 roots. Some of them might be real, and some of them might be imaginary, but we're guaranteed to get that many roots out of that degree. Okay, what is Descartes' rule of signs? It's basically a way to tell you what kind of zeros you would expect to find. So here's a very simple example. Let's suppose we had x squared plus 7x plus 12 equals to 0. Descartes' rule of signs is you can tell how many positive zeros you're going to have and how many negative zeros you'll have based on these rules. The number of changes in the sign of the coefficients of the terms, or less than that by an even number. So that's kind of a mouthful. We'll talk about that. And then for the number of negative zeros, you're going to have the number of changes in the sign of this. You have to plug in a negative for x and see how many times the sign changes. So let's just demonstrate that with a real simple example. This right here factors to x plus 4 times x plus 3, which means it has 2 negative zeros. It has negative 4 and it has negative 3. So according to what Descartes is saying, the number of negative real zeros is the same as the number of changes in the sign of p of negative x. So if this were our polynomial right here, we have to evaluate p of negative x. We have to plug in a negative x for every x there and see how many times does the sign change from positive to negative. So let's see how that works right here. If we plug in negative x right here, if we plug in negative x, we're going to get this. We will get negative x squared, the whole thing squared would be x squared. 7 times negative x would be negative 7x. And then we have that plus 12. Okay, how many times does the sign change here? Well, this is going to be a positive right here because that's a positive 1. That's what that means, by the way. It says the number of changes in the sign of the coefficients. Coefficients means the numbers in front of the x's. So that's a positive 1. This is a negative 7, so there's one sign change. And that's a positive, so that's another sign change. So we have 2 sign changes. That means, according to this rule, we could have 2 negative zeros, or we could have less than that by an even number. So we could have also 0 negative zeros. And in fact, we do have 2 negative zeros. That matches up. Okay, when he says less than this by an even number, that means if you did that test and let's say you wound up with 8 sign changes, that means you could have 8 zeros, or you could have 6, or you could have 4, or you could have 2, or you could have none. So that each possibility is to have that number of zeros or less than that by the number, by basically a multiple of 2. Alright, let's test it with a more complicated equation just to see how this works. We want to know how many positive zeros could we have, and then how many negative zeros could we have. Positive zeros is easier to find because all we need to do is just count the sign changes. So we have a positive, that's still a positive, that becomes negative, negative, now there's another sign change, that changed, and that changed. If we count the sign changes, there's 1, there's a second change, there's a third, there's a fourth. So that means we could have 4 positive zeros, or we could have 2 positive zeros, or we could have no positive zeros. Okay, any one of those is possible. So we're asking for positive real zeros. We'll get to imaginary zeros in just a sec. So for negative real zeros, what we need to do is slightly more involved. We need to find, for negative zeros, we need to plug in negative x and see what happens. We'll plug in negative x for all these things up here that have x in them, and we'll see what happens when we do that. So just plugging in negative x for all those x's, we have minus 4 times negative x to the fourth, minus 6 times negative x to the third, plus negative x, the whole thing squared, and then we have minus 8x plus 5, so minus 8 times negative x. Again, all I'm doing is taking the original function, and because we're seeing the test for negative 0 says plug in negative x and see how many times the sign changes. So negative x, or any negative to an even numbered power, is going to be positive, so that's positive. Any x to an odd numbered power will be negative, so that becomes minus 3x to the fifth. This becomes minus x to the fourth, because this thing is positive, but it was already a negative 4 there. This thing will be negative, times a negative will be positive. Negative x squared will be, the whole thing will be positive x squared. Negative times negative will be positive 8x plus 5. So let's see how many changes there are. That's positive, that's negative, still negative, changes to positive, 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 positive. So it looks like we have one change, second change. That means we could have 2 negative zeros or no negative zeros. And by the way, the number of total zeros, if we remember that theorem, the number of total zeros should be 6. So here we could have 4 or 2 or nothing. Here we could have, for negative zeros, we could have 2 or nothing. And then imaginary zeros, only thing we know is this. We know that it has to be an even number. So if all the zeros were imaginary, we could have 6 imaginary zeros. Or we could have 4, or we could have 2, or we could have none. That's all we know. We have to actually solve further to be able to figure out how it works. Okay. And this is just a kind of a table showing a summary of what we just talked about. So the number of, these are different combinations. We know in that last one we would always have 6 zeros because it was x to the 6th power. Here's the way combinations could work out. We said the positive zeros could be 4, negatives could be either 2 or 0. So this is how that situation would work out. Or because the positives could be 4 or less than that by an even number, we could have had just 2 positive zeros. And then here's other situations that would get us to 6 zeros. So anything in that table is a possibility, and obviously to narrow it down you need to solve further. Alright, let's try this one. So it says use synthetic substitution to find zeros. Now if you look at this, there's no obvious way that this would factor by grouping. So the easiest way to do it is just, and this is not ideal, we'll talk about other methods to do it first. But let's first do this right here. Let's determine what kind of zeros we're trying to find. That will at least help us narrow it down. So first of all, there should be 4 total zeros, because that's x to the 4th. And that means there could be 4, 2, or 0 imaginary zeros. We know it has to be an even number. So any of those are possible. In terms of positive zeros, let's just count the sign changes. That's positive, negative, positive, positive. So it looks like there's 1, 2 changes. So we could have 2 positive zeros or less than that by an even number. So 2 or no positive zeros. For negative zeros, let's plug in negative x for all these and see what happens. Let me just erase this. If we plug in negative x right here, if we plug in negative x to the 4th, we would get, raising something to the 4th power that's negative, we get positive. If we plug it in right here, we would still get positive, but it's times negative 18. And then if we plug in negative x right here, that becomes negative. And then we still have that plus 80. So that's positive, that's negative, negative, positive. So there's 1, and there's 2 changes. That means we could have 2 negative zeros or no negative zeros. Okay, now how do we actually solve it? Because it says find all the zeros. So we know that's what we're looking for. Here's the easiest way to do it, at least for this problem. What they suggest is just plugging in different numbers. We know that we're looking for potentially 2 or no positive and 2 or no negative. So what I've done is put that equation into the calculator. And I go to second graph, which is second table. And then it gives you basically a table of all the numbers that you would get when you plug in to that function. So we can see right away, if we look at negative 2, that's a 0 right there. And also negative 4. So negative 2 and negative 4, we could use either of those. So let's use, when they say synthetic substitution, that means using synthetic division. So let's do that right now to just narrow this down. So when we plugged into our table, we had zeros at negative 4 and negative 2. So I'm just going to take this equation, and we'll use negative 4 as our first example. That represents x plus 4. If you plug in negative 4 for x, you get a 0. Okay, so let's plug this in, and we'll use these coefficients. So 1x to the 4th. I'm just going to add all of these powers up here so we can see 1x to the 4th. So 1 goes there. There's no x to the 3rd, but we need to include it in our table because you can't skip powers. The coefficient from x squared down here is negative 18. There's the negative 18. We have a 12x, and our number, our constant term, is 80. Synthetic division, what we do is we add these columns. So 1 plus, there's nothing there. So 1 plus nothing is 1. And we take these numbers down here and multiply by negative 4. So 1 times negative 4 is negative 4. Add the columns. Negative 4 times negative 4 is 16. Add those columns. Negative 2 times negative 4 is positive 8. Add the columns. 20 times negative 4 is negative 80. And sure enough, we get a remainder of 0, which is what we were supposed to get, because that is we already saw from the table, that's a factor, that's a 0. And now we get something called a depressed polynomial. So that was x to the 4th. That means this is x to the 3rd right here. This was x to the 3rd. That means x to the 2nd. And all of these powers go down by 1, basically. Okay, so we saw negative 4. That's our first 0. Now let's use negative 2. We'll reduce it even further using negative 2. So same thing with synthetic division. We'll add these. 1 times negative 2 is negative 2. Add those to get negative 6. Times negative 2 would be 12. Add those to get 10. 10 times negative 2 is negative 20. And again, we get a remainder of 0. This started as x cubed, so now it's x squared. That started as x squared, now it's x, and that's just a number. So now we have this. We basically have x plus 4, that's coming from this negative 4, times we have x plus 2, because that's coming from this right here. If you plug in negative 2, you get 0. And now this is what's left. We have x squared minus 6x plus 10. We need to find 2 more zeros out of that. And the easiest way to do it is probably using the quadratic formula. So a is 1, b is negative 6, and c is 10. So let's just plug in those numbers to the quadratic formula, and we'll see what we end up with. So we have negative b, so negative negative 6, plus or minus b squared, that's negative 6 squared, which is 36, minus 4 times a was 1, times c is 10, all over 2 times a, or 2 times 1. And then let's simplify that. We would get 6 plus or minus 36 minus, this whole thing is 40, so 36 minus 40 is negative 4. The square root of negative 4, that's the same as the square root of negative 1 times 4. The square root of 4 is 2, and the square root of negative 1 is I. So that's the same as 6 plus or minus 2i over 2. And if you split this down the middle, 6 over 2 is 3. And 2i over 2 is I. So there's your other 2 zeros. We have 3 plus I, 3 minus I, and the other ones that we found before were negative 4 and negative 2. And that matches up because this was a 4th degree. It was x to the 4th, so we should have 4 zeros. Let's see if it agrees with what we said. We have 2 imaginary zeros, and that was one of the possibilities. And we have 2 negative zeros, and that was also one of the possibilities, because we said the negative zeros could be 2 or none. It turned out to be 2. Alright, last thing in this section, we want to learn how to write a function given the zeros. And there's something called the complex conjugates theorem. What that basically says is if you know one of the complex numbers that's a 0, if you know, for example, 4 plus 6i is a 0, then it's guaranteed that its conjugate will also be a 0. 4 minus 6i will also be a 0. So for example, if I know that negative 2 plus I, if I know that's a 0 of a function, I know that negative 2 minus I is also a 0. The name for that is called the complex conjugates theorem. That's helpful because if we know one 0, we get another one for free, basically. Okay, how do you do what we're about to do? Well, if I told you, for example, that x equals 1 and x equals negative 2, if I told you those were zeros, what you could basically do is figure out what function has those as zeros. So if x equals 1, if I plug in 1 for x, I would have to subtract 1 from it to get a 0. Same thing, if I plug in negative 2 for x, I'd have to add 2 to get a 0. Now if I multiply this out, that would be the function that has those as zeros. So that's basically what we're going to do right here. Okay. Let's actually try this one first. This one's a little bit harder. Okay, we want to write a function that has those as zeros. And here's the thing, they don't tell us this, but we do know that if 2 minus 2i is a 0, we know that 2 plus 2i has to be 0 also. And we know that if 1 plus 2i is a 0, 1 minus 2i also has to be a 0. So let's write this function. Negative 2, by plugging negative 2 for x, I would have to add 2 to get a 0. And then I have 4 other zeros here, so this is actually going to be a 5th degree function. So we're going to have x, it's always minus the 0, so x minus 2 minus 2i, that's this one. And we have x minus 2 plus 2i, that's another 0 from right here. And we have x minus 1 plus 2i, and we have x minus 1 minus 2i. Now, once we have that function, we can now start to simplify by multiplying this stuff out. And it starts to get a little bit messy, but once you do it a couple of times, it's not so bad. So here's the strategy for both of these. Let's start with this one. We want to distribute the negative. So x minus 2 plus 2i. And this one, when it's distributed, becomes x minus 2 minus 2i. Same thing right here. When you distribute the negatives here and here, this comes out to be x minus 1 minus 2i. X minus 1 plus 2i. Okay, here's a way that we can make this easier to multiply for us. If we look at this right here, we have something, we have x minus 2 plus 2i, and we have x minus 2 minus 2i. And that might remind you of something we talked about before called the difference of squares. The pattern is it's something plus a number, something minus a number. So let's just substitute the letter a in for x minus 2, because that will be easier to see what we're doing. We'll substitute a, and we'll put that back at the end. Same thing here. This is x minus 1, so let's just substitute the letter b in here, because that will be easier for us to multiply. Then we have b minus 2i, b plus 2i. And now let's just kind of FOIL this out here. So we have x plus 2. If we FOIL this thing out, a times a is a squared. A minus 2i minus 2ai plus 2ai, those are going to cancel because they're a difference of squares. And then plus 2i times negative 2i is minus 4i squared. Same thing over here, b times b is b squared. The outer and inner terms will cancel. Minus 2i times plus 2i is minus 4i squared. And that's still equal to 0. Okay, let's keep simplifying this. So we have x plus 2. Remember that I squared is a number, that's negative 1, so that's like minus 4 times negative 1, which is another way of saying plus 4. And this is the same right here, b squared plus 4. Okay, we're almost done. Now we just have to go back and recall what did we substitute. So a, up here, a was equal to x minus 2. That's coming from right here. And b was equal to x minus 1, so let's sub those back in. Just write that right here. A was equal to x minus 2, b was equal to x minus 1. And that's, again, coming from here, so let's plug those back in. So we have x plus 2 times a was x minus 2, so now we're going to have x minus 2 squared plus 4. And b was x minus 1, that squared plus 4. Now when we FOIL this stuff out, we're going to have x plus 2. When you FOIL x minus 2, the whole thing squared, you get x squared minus 4x plus 4, and then we still have that plus 4 there. Same thing here, when you FOIL out x minus 1 squared, you're going to get this right here, and we still have that plus 4. And then we just have to simplify a little bit more, so we still have that x plus 2. This, when you add 4 and 4, you get 8, so x squared minus 4x plus 8. This right here, x squared minus 2x plus 1 plus 4 would be plus 5. And we're almost there. I know I've said that a couple of times. This is definitely a longer problem. Now let's just distribute this out. So we're going to have x plus 2, and we'll distribute this whole thing right here. So x squared times each of these terms will be x to the 4th minus 2x cubed plus 5x squared. You need a bigger parentheses there. Okay, now when we distribute the minus 4x to each of these, we're going to get minus 4x squared. Minus 4x times minus 2x would be plus 8x squared. Minus 4x times plus 5 would be minus 20x. And then last one, we have 8 distributed to each of these. That's 8x squared. 8 times negative 2x is negative 16x, and 8 times 5 is 40. Okay, and I guess the very last thing we could do is just simplify by combining the like terms and then distribute the x plus 2 also. So let's see if we can simplify this. So x to the 4th doesn't have a like term. Neither does minus 2x cubed. We have plus 5x squared minus 4x squared plus 8x squared plus 8x squared. If you combine all of those, you would get 17x squared. Okay, then we have, what's next? We have the x terms. So we have, where are those? We have minus 20x minus 16x, that's minus 36x. And we still have that plus 40. And here's the very last step. Let's distribute the x to each of these things right here. And we will have our final answer. So x distributed to each of these will be x to the 5th minus 2x to the 4th plus 17x cubed minus 36x squared plus 40x, and then we distribute the 2 to each of those also. So the 2 distributed to each of these will be plus 2x to the 4th minus 4x cubed, and then plus 34x squared, that's 2 times 17x squared, so plus 34x squared. Again, all I'm doing is taking this 2 and multiplying it by each thing. So 2 times negative 36x is minus 72x. 2 times 40 is plus 80. And let's just simplify that. So we're going to get this. We get x to the 5th minus, we have minus 2x to the 4th plus 2x to the 4th. Well, those cancel each other out. You have plus 17x cubed minus 4x cubed. That's going to be plus 13x cubed. You have minus 36x squared plus 34x squared. That will be minus 2x squared. Then you have 40x minus 72x, that will be minus 32x, and then you still have that plus 80. So believe it or not, this polynomial right here, that big mess, has 5 zeros, because it's x to the 5th, and the 5 zeros are the ones that we started with way up here. So that is section 5.7. It was certainly some of those problems are a little bit more complicated, but as you practice and as you become more familiar, it starts to get easier.